Alrighty, it's about 7:05. I think it's a good time to get started. So hi everyone, thank you for attending this evening's AIAA webinar. My name is Kiana and I will be your host this evening. We have a really exciting talk tonight, and before we begin, I would like to let everyone know that there will be a Q&A session following Ian's presentation, so please use Zoom's Q&A feature located at the bottom of the screen if you would like to ask a question. Without further ado, please let me introduce our speaker, Ian Dargin. Ian Dargin has over 50 years of experience in R&D, including systems engineering, space science research, and project management, working on large high-tech programs with leading aerospace companies, the DoD, and NASA. He is a former Air Force officer with 22 years of service. He served the U.S. Air Force Space Test Program Office at Space Division Los Angeles Air Force Station. He has attended the National Test Pilot School for Flight Test and holds an FAA pilot's license with an instrument rating. He is also past chairman from 1999 to 2000 of the New England Council of AIAA. He received a master's in administration from Central Michigan University, a bachelor's of science from Parks College of St. Louis University, and an associate's degree in engineering from Wentworth Institute of Technology. With the emergence of commercial space opportunities and growing space activities, management of orbiting debris is becoming a serious concern. He holds the U.S. patent for PRRISM, a novel approach to remove space debris in near-Earth orbit by operating outside of debris orbits and using solar wind. His article, Method and Apparatus for Removing Orbital Space Debris from Near-Earth Orbit Using the Solar Wind, Platform for Redirecting and Removing Inert Space Material, PRRISM, is now published in the Journal of Space Safety Engineering and available online. Today, Ian will talk about his work on PRRISM and how it can be used to solve one of the largest challenges in the aerospace industry today. Ian, please begin when you're ready.
Well, thank you, Kiana, for that introduction, and thank you all for attending this webinar. It's my pleasure to be a part of this. I got started and followed the the space program way back and during the Apollo days, and I feel the excitement again from all of the commercial involvement. My name is Ian Dargin again, and I'm principal for IronStar Engineering. IronStar Engineering was originally founded in March of this year in Delaware, and as Kiana said, I had 22 years with the Air Force. One of my duty assignments was with the Space Test Program Office, working on a joint DoD and NASA space science mission called CRES, where I was project manager and co-chair of the experimenters working group. It was during that time that I developed an interest in this debris problem and worked on it off and on over the years. And then the last 3 years, I devoted full time to working on the patent. So the topic tonight is method and apparatus for removing orbital space debris using PRRISM and the solar wind. In the outline, these are the topics I'll address. I'll talk to the space debris problem. I'll cover PRRISM functions kind of as an intro level, and then I would discuss solar wind characteristics, polar cusp reconnection, and then we'll talk about the PRRISM operation. And I'd like to spend a little time just discussing the gravimetric force on small particles. And then we'll finish up with a summary and then open it up to questions. So the pie chart, this is provided from the European Space Agency, showing that fragmentation material is the largest percentage of this debris, and followed by non-functional spacecraft, rocket bodies, mission-related items, and debris of unknown sources. Now, I'll just put this out there now. The debris, the types of debris will require multiple solutions. It's just, there's too much of a difference in size to have it all be handled with one solution. So we have over 19,000 objects that are being tracked by the Air Force Joint Space Operations Center. And these objects are all greater than 10 centimeters, which currently is the limit as to which you could actually track. Now, the 10 centimeters is roughly the size of a softball. If we consider that the size down to 2 centimeters, which currently is being looked at by at least one company, Leo Labs, then the amount of debris is up over 1 million. Now, these pieces travel at roughly 9 kilometers per second, or 6 times the speed of a rifle bullet. Many orbits, and as you can see from the image, sun-synchronous orbit, which is a polar orbit, is considered to be the most populated. But there are many others. And if you look at the image, the near solid ring in white is considered low Earth orbit. Now, this is not to scale, but yet it's just to show that there is quite a bit of debris out there, and various orbits from the elliptical at 0 inclination to polar at 90 degrees, and various inclinations and altitudes in between, as well as elliptical orbits. So contributing to this has been several key events. In 2007, the Chinese conducted an anti-satellite test and added about 3,000 pieces of debris. And studies have shown, or at least reported in the NASA Orbital Debris Quarterly newsletter, that only 2% of that debris was removed after a 2-year period. And then there was another in 2009, the Russian Cosmos satellite collided with an Iridium satellite, creating more debris. The United Nations has some guidelines, but it's estimated that only 50 or 60% are compliant. Now, that may have improved a little bit, but we still don't have any regulations or oversight other than just providing these guidelines to operators to remediate and mitigate additional debris. Now, there's one study that was conducted with the direction of the United Nations, and that study was made by 6 different countries, and they all concluded independently that active debris removal would be necessary in order to prevent what is referred to as the Kessler syndrome. Don Kessler is a NASA scientist who had done quite a bit of studying on this phenomena, and actually stated that the syndrome basically would be the reason why orbits might be unusable, that the more objects you place in an orbit, the probability of a collision increases to the point where you'd have a domino effect, and more debris would beget more debris, and thus closing down that particular orbit. I wanted to just mention that because of new and growing uses for low Earth orbit, we have constellations being proposed in the order of 500 to 1,000 or more for low Earth orbit. Low Earth orbit is the most populated right now, but because of new technology, there's a reason to push for these large constellations. Not only that, we have the CubeSats, and we have the entry of tourism pretty soon. We depend on these satellites for a number of things: navigation, communications, and weather, principally, but there are many other uses. And as we increase the opportunity for men in space, the error margin will increase, and we will have to have a larger bubble of uncertainty, if you will, around known and trackable debris. So that said, we have a number of different mitigating concepts that have been proposed. I'd say most, if not all, require operation within the orbits themselves, contributing or possibly contributing to the debris problem. PRISM, on the other hand, does not. PRISM operates outside of that debris orbit. So Basically, PRISM is a platform that remains outside of the debris field. It's a platform for redirecting and removing inert space material. PRISM would operate from an elliptical orbit at around 10 Earth radius apogee above the polar cusp. From that point, it would supplement additional energy in terms of electromagnetic wave to act on the solar plasma as it enters the polar cusp. And it would control the flow in the polar cusp by increasing its density, reducing the turbulence, and by means of constructive interference, increase the force and the exit force at the exit of the polar cusp. It would also create a 3D intercept solution with the space debris in low Earth orbit, and then removes the debris with an increased pressure force. Now, there's been a number of science satellites that have been on science missions measuring different characteristics of near Earth orbit. And this is, everything is in terms of Earth radius. So you have the low Earth orbit and geosynchronous relative positions to the polar cusp and the Van Allen belts. Okay, so we have the solar wind is in the shape form of a Parker spiral. It's been referred to as a ballerina skirt. It comes in as a toroidal flow outward from the sun. It's also been referred to as a magnetic spaghetti with magnetic flux tubes surrounded by current sheets, 35 to 100 Earth radius in diameter. And if you remember this, I'll refer to this later on, but the Earth, as this toroidal sheet moves outward from the sun, the Earth and various planets find themselves in either a trough or a ridge, so that the flow of this interplanetary magnetic field within the solar wind affects the Earth's geomagnetic field differently. So the composition has been reported as 96% protons and 4% helium plus ions. There are two distinct speeds, 350 kilometers per second emanating from the solar equatorial region and 800 kilometers per second leaving from the polar areas of the sun. The polarity is shifts so that at the end of the solar cycle, at solar max, the polarity will flip. Looking at the area, I devised just a sketch here to show that I'm using the thickness as presented in Wikipedia as far as the thickness of the solar wind, but using the width to match up with the 10 Earth radius position that I placed the PRISM satellite in. So we have an area calculation. Now this is all prior to Earth, so I wanted to use that as a comparison. So we'll calculate again for the exit of the polar cusp. But this is prior to the polar cusp. I'm calculating mass flow using the slower solar wind speed and dynamic pressure. And I won't go through these numbers, but you feel free, these are on my website. You can access these charts on my website at ironstarengineering.com. So the velocity I'm using here is 350, the slowest speed, and we get a dynamic pressure of little less than 2 nanopascals. The solar wind force, and this is again prior upstream of Earth, is 2360 newtons. Polar cusp reconnection is, as I mentioned when we were talking about the Parker spiral, the reconnection process is very turbulent and dynamic. It goes from a very smooth flow to within the Earth's geomagnetic field to very turbulent. So the IMF orientation that I mentioned during when I was showing this Parker spiral is very important. So you could see a flow from south to north as it approaches Earth, or it could go from north to south. And the flow direction, the orientation of the IMF is more important, the most important characteristic for the reconnection process, more so than the difference in speeds. The turbulent flow exists within the polar cusp because of the reconnection and the distribution of the electrical field and the magnetic field along with the magnetic field. It has been recorded by several science missions, Hawkeye and IMP-8, to name a few. And just to orientate you, the flow would be coming from the left side of your screen. The Earth would be rotating counterclockwise. So, and I've indicated with a plus, an arrow going into the page, that would be going from dusk to dawn, and then several dots, although they're missing here, would show an arrow out of the page going from dawn to dusk. But suffice to say, there's quite a bit of turbulence been reported and measured in the polar cusp. And one other indication of the disturbed flow is the presence of O+ ions higher up in the polar cusp, which originate from the ionosphere. The density remains fairly consistent at roughly 9 per cubic centimeter, very much the same as what we saw prior to Earth in the free stream solar wind. But as you get down below full Earth radius, the density increases to up to from 100 to 200 per cubic centimeter. This is taking a look at the exit area of the polar cusp and the force that would be available at the exit of the polar cusp. And I'm using a definition provided by Maynard, and that is, in the ionosphere, the cusp is several hours wide and several degrees in depth. So on the longitude, the 79 to 81 degrees comprises the length value, and then we will use on the next screen the computation for just the 2 hours out of 24. So we're calculating an area that basically is the size, cumulative size of Maine, New Hampshire, and Vermont. Looking at the mass flow, and I've upped the particle count to 15 just as a conservative value, and the velocity I've pegged it at 100 kilometers per second. Again, as I say, this is estimated values, and I'll talk about that a little bit later. Again, pressure, dynamic pressure, polar cusp is 1/4 of a nanopascal. And you can see a force of 32 newtons at the exit of the polar cusp. Now then, taking a look at the variation as a result of an improved velocity flow at the exit of the cusp. And you can see there's a significant change in newtons as we go higher in velocity. Now, the operation of PRISM consists of 3 separate satellites. Now, the solar wind will be flowing from left to right. The normal flow, the smooth flow, laminar flow about the magnetosheath is evident. And as we get closer in and the Earth's geomagnetic field interacts with the interplanetary magnetic field, we start to get the turbulent flow. They also showing is the Van Allen radiation belts, the northern and polar cusp, and the normal flow in through the polar cusp contribute to the northern and southern lights. Now we have a solar plasma sensor upstream of Earth, recording key parameters of the solar wind. And we have the space debris sensor located much closer in and tracking debris in Earth orbits. With PRISM located at 10 Earth radius, we're going to start the process by a ground command signaling to PRISM to activate and align itself with the polar cusp, creating an electromagnetic wave, also to align itself and to make the electrical field and the magnetic field identical to what the SPS sensor is indicating as far as the solar wind goes. This also taking the data from this SPS as far as solar wind speed and other characteristics, and using the data from the space debris sensor, coming up with a target intercept. And this will be done by the targeting computer. So that from the command, we would have the alignment, and we would have the electromagnetic wave matching the incoming solar plasma, and then adding to or supplementing to the flow through the polar cusp, creating a denser and more aligned and less turbulent flow, increasing the exit force and density when it reaches the intercept point for the debris. And the next slide will show a two-dimensional view of that, where we have a increased flow through the polar cusp, reaching the intercept point at the same time as the debris reaches it, and it is slowed down enough so that it will deorbit or drop to a lower orbit. Just putting this in words, we have initially the position of the PRISM is over the entry point of the polar cusp. PRISM receives parameters from the SPS of the solar electromagnetic wave. It also receives parameters from the space debris sensor on the debris. The targeting computer on board PRISM would calculate the intercept and activate PRISM's electrical and magnetic fields and frequency to match the incoming solar wind. Direct the local EM wave from PRISM to interact with the solar wave at the polar cusp entry. And finally, the local EM wave interacts with and converts a turbulent solar EM field to a laminar EM wave to maximize the dynamic pressure and force at the polar cusp exit. Now, important to understand the forces on the particles themselves. So I've chosen a 2 centimeter diameter particle, just an example. And this is using an equation that Don Kessler came up with based on observing breakups and area to mass calculations to go from a diameter of a debris particle to a mass. And for the 2 centimeter particle, we have a mass of 7 grams. And using that with the gravitational force equation and showing that we would require a force of 0.06 newtons for that 2 centimeter particle to remain in a 500 kilometer orbit. Now, looking at the debris diameter versus gravitational force, the table shows that as we increase in diameter, the gravitational force increases considerably. So this plot of gravitational force versus orbital distance, it's clear that as you move outward from the Earth in higher orbits, the gravitational force decreases. And if we were to take a look at a specific orbit, say the 500-kilometer orbit, we would be at 6.8 roughly on the screen. And the top curve would be the 200-centimeter debris. The next one down, the magenta, would be 150 centimeters, and then the light blue would be 100 centimeters. So on that curve, it's less than 500. So you would be able to, if we had the 350 kilometers per second speed, it's conceivable that you could have a force near the amount required to remove the 100-centimeter piece of debris. But again, this would all need to be tested. So in summary, PRISM operates outside of the debris orbit, so it's not risking the possibility of causing more debris. The turbulent flow is present in the polar cusps. That is across the board. Each of the science reports, those that have flown from Hawkeye and IMP-8, they've flown through polar cusp, and they're all reading that there is turbulent flow in the polar cusp. And this is due to the solar plasma magnitude and direction, along with the magnetic field has reduced the downward flow. It seems to me that the sufficient force is available at the exit of the polar cusp to remove small pieces of debris. The uppermost level of that debris size would be needed to be tested. Now, I also want to point out that the data that I've used from different science missions is simply a snapshot in time. So, and for specific orbits and for specific altitude. Although Hawkeye has taken data through the polar cusp, it is basically a snapshot or just a window, and the solar cycle as well. So the time of that mission was during a specific phase of the solar cycle and doesn't cover the entire solar cycle. It's important to note that with the growth and our dependency on satellites, we need to be aware that although the probability of a collision is low, the effect of a collision or collisions could be catastrophic with regard to our day-to-day communications, navigations, weather, and other uses for the satellites. Consider also the tourism trade, where we have to increase the margin of safety. And you have a situation that needs to be addressed fairly quickly. With that, I will end on a note, a quote from Star Trek: "One man cannot summon the future, but one man can change the present." And I open it up to questions, and thank you for listening.
Alrighty, Ian, it looks like Chris Clark has a question. He asks, how much power is needed to operate PRISM when targeting a single debris object? What about if PRISM were operating continuously?
That's a good question. The power would be as needed. So as you can see, the force required to remove some of the small pieces of debris is very small. And would be measured, the amount of power would be measured as far as what debris you're going after. I'm looking at it from a force standpoint, and I'm thinking we could probably go after debris as large as 100 centimeters in diameter. And in fact, we might be able to go even greater. What I'm looking at as well, do we have an equal force to offset the gravitational force requirement for that particular orbit and that particular size of debris? If we could say, provide a force maybe only 50% of that gravitational force requirement, would that slow it down enough, cause it to decay in its orbit, and therefore we can go after larger pieces of debris? But putting a question on the power, it's uncertain at this time, and I'd have to say that additional testing would have to be made to determine that. Does that answer your question?
All righty, we have another question from Sean. Yes. Wouldn't the force on the PRISM satellite be the same as the force on the debris?
I'm not sure I understand. What we're trying to do here is create an electromagnetic wave that accelerates the flow and eliminates the turbulence, while also increasing the density and exit pressure at the exit of the polar cusp. The electromagnetic wave, unless you're anticipating a opposing force somehow on the satellite, I think that what we're after here is reducing the turbulence in the polar cusp, so that we can come up with a higher force level at the exit of the polar cusp.
All righty, thanks, Ian. So Avi asked a question. They ask, how do you target a single piece of debris and make sure you don't miss? Would it only hit the debris when it travels through the correct location at the exit of the polar cusp? That is it an instantaneous force? Also, does it come at an orthogonal direction to the velocity of the debris? And if so, what slows the debris down in order to deorbit?
All right, a loaded question. I'm sure. Well, let me take it one at a time. The debris would be in a field of debris. So first of all, consider a missile intercept solution. So a 3D missile intercept, you would be using the information received from the space debris sensor to create an intercept point for the solar wind. So the entire operation would be triggered once the ground command signal had been sent to PRISM to take the data from the SPS, the solar plasma sensor, and the space debris sensor, and create an intercept solution, a 3D intercept solution. So first of all, it's dependent on the ability to detect the size variation in the debris, but I'm imagining that we're having a cluster of debris pieces that we're targeting, but this can be pulsed or it can be a steady electromagnetic wave. But the concept here is to come up with a higher force at the exit of the cusp to push the debris into a decaying orbit. Now, an orthogonal force on the debris will not really work. It has to be an opposing force. It doesn't have to be much, but an opposing force would be required to actually slow the debris down. And again, you're working with a cluster of debris. So, and imagine you've got debris that goes from, say, 2 centimeters up to maybe 200 centimeters, all in the same grouping. Well, the force, and this is going to probably occur over time, and again, testing needs to be done to prove this, but you can actually, with a given force, affect the removal of some of the smaller pieces, but then you may have to up the power, to someone else's earlier question, to get a higher force to work on that larger pieces of debris in that group. And certain orbits may not be reachable. That's something else that needs to be looked at. We're talking about a problem that requires multiple solutions. I mean, there is a company, I can't think of the name of it right now, but they have a means to remove a derelict satellite, but they're not addressing the small stuff. So we've got to categorize how we're going to approach this debris problem. Now, Kiana, did I miss? Was there any aspect that I didn't address?
Let's see. I think you answered all the parts of the question. Abby, if you have anything, just put it in the chat and I'll come back to it. So I have another question from Brett DeBlanc. They ask, is it correct that the basic mechanism is to expand the cross-sectional area of the polar cusp during operation of PRRISM? If so, can you talk more about the physics of this mechanism?
Yes. No, it is not the objective to increase the cross-sectional area. I used the area to show a comparison between the upstream solar wind force prior to the Earth and the force at the exit of the polar cusp. So.
And I have one more question from Brett. They ask, what % of estimated small debris goes through the regions affected by this solution?
I'm sorry, Kiana, could you repeat that?
What % of estimated small debris goes through the regions affected by the solution?
I have to refer you to the sun synchronous orbit. The sun synchronous orbit is a polar orbit, and it is the most populated with debris, most populated all in total. As far as a percentage of the overall debris in orbit, I'm sorry, I would not. I'd just be guessing. I don't know what that would be. I think that the approach would be a prioritization. In a workable solution, we would have to go after the most populated. Maybe there'd be a hierarchy of reasons where you might want to say, well, this is critical for navigation, or this is critical for communication, so we need to make sure that this orbit is clear. Or we're going back and say that, well, all right, there's this orbit is almost close to being overcrowded, and the chances of a Kessler syndrome here is high, so we've got to go after this particular orbit first. So somewhere along the way, we're going to have to prioritize what's important and what we're going to go after first, and then take it a step at a time.
So Brett also asked a follow-up question as an alternative. Which orbits does this affect?
Sorry, which part?
Which orbits does this affect?
Which orbits? Yes, primarily because of the placement of PRISM. We're talking mostly polar orbits, but I could say that some of the high inclination orbits could also be reached. And I haven't gone into a lot of the detail on these orbits, but since the polar orbit, sun synchronous anyway, is the highest in populated debris and objects, we would get a lot of bang for a buck in that regard. And we could work towards getting the debris in some of the higher inclination orbits, 60, 70, 80 degree. Again, testing would be needed to prove that out.
Alrighty, Chris Clark asked another question. He says, very interesting concept. Thank you for presenting and also for answering my earlier question. Is it known what size spacecraft would be needed for PRISM? Large satellite, small satellite, CubeSat, etc.? Does the required EM wave emission instrumentation already exist? What would the effective range be for PRISM in proximity to the polar cusp?
Good question. We're the range. Well, first of all, let me say that the solar plasma sensor information instrumentation is available. We've seen that used on many science missions. The space debris sensor, again, I think we can take a lead from what's been used on the ground, but certainly that would be available as well. As far as PRISM goes and the distance and the effectiveness and how much loss there would be from PRISM's orbit to the polar cusp, again, needs testing. That's my focus right now, is to get to collaborate so that I can raise some funds to look into some of these cases further. But again, that answer I do not have as far as the power and maybe the losses from a 10 Earth radius. What is the power loss from that 10 Earth radius down to the exit at the polar cusp in the ionosphere? I don't have the answer to that.
So I don't see any more questions at the moment, so I think that can wrap up the session.
All right, well, I thank you very much for attending, and I really appreciate the questions. I think that we need to continue this discussion and dialogue, and if not PRISM, there's going to be other solutions that will be available, but multiple solutions will definitely be needed in this case.
Great, thank you so much, Ian, and I would like to thank everyone for calling in this evening, and everyone have a good night.
Thank you very much, Kiana. Appreciate it.